Hi everyone, welcome to our lecture on conditional probability. Remember that in the last lecture, we started to see the rules from which we're going to build our inductive logic, or namely, our probability theory. Today we're going to give you some new definitions and some new rules, and we're going to prove some interesting things. So let's get started. So let's start by refreshing our memory on the 5 rules that we have seen. The first, which might be the simplest, is that tautologies get assigned probability 1. So remember, if a statement is always true, then that statement is certain, so we're going to want to assign it probability 1. The second rule that we saw is that self-contradictions get assigned probability 0. You might think that this is kind of the opposite of rule 1. So if a statement is always false, then it's impossible for it to happen, so we want to assign it a probability 0. The third rule is that logically equivalent statements get assigned the same probability. So if two statements are equivalent, so if they mean the same thing, then we want to assign the same probability to them. The fourth rule is that if two statements are mutually exclusive, then the probability of A or B, assuming that A or B are mutually exclusive, is equal to probability of A plus the probability of B. And the fifth rule that we saw is that if two statements A and B are independent, then the probability of A and B is equal to probability of A times the probability of B. Great. So in today's lecture, what we're going to do is we're going to see the notion of conditional probability, which might be new to you, and we're going to show the law of total probability. So let's get started on conditional probability. So as usual, it helps to start with an example. So suppose I roll a fair 6-sided die behind a screen. So I roll the dice, and you can't see the result, but I can. You can't see the result, but I tell you that's an even number, and you have no reason to think that I'm lying to you. I'm not lying to you. Okay, so I see what the die lands on, and I tell you it's even. And then I ask you, what is a probability that the die is also a high number? So either a 4, a 5, or a 6. Try to write this down and think about it and put a number to it so that when I give you the answer, you can see if it corresponds to the right answer or not. Okay, trusting that you did this, you might be surprised to find that the result is 2 over 3, so 2/3. Now, why is that? Let's see. So here's a visual representation of the possible values that the die can have. So 1, 2, 3, 4, 5, 6. Now, remember, I told you that the dice landed on an even number. So you know that the die landed either on a 2, a 4, or a 6. And then the question is, what's a probability that's also a high number? And so here, the only two possibilities are 4 and 6, shaded in blue. So that's the intuition for why it's a 2/3 probability that it also landed on a high number. This is how we're going to look at conditional probability, is that you're given a condition and you restrict the probability under that condition. Let's see a more formal definition. The probability of A line B is how we're going to denote the probability of A given that B occurs, right? This is not the same as the probability of A and B, because here we're going to assume that B actually occurred. So similar to how we assume when trying to determine if a deductive argument is valid, we assume that the premises are true. Here we're going to assume that B occurred. And so how do we figure out this probability? Well, we have the probability of A given B is equal to the probability of A and B over the probability of B. You should really learn this formula, and this is the definition of conditional probability. And note that if the probability of B is equal to 0, then the conditional probability is undefined. So we're always assuming that the probability of B is greater to 0. So it's not a self-contradiction, for example. Now let's look visually why we want this definition of conditional probability to be this formula, which might look a little complicated to start out with. Okay, so let's look visually why we want the probability of A given B to be equal to the probability of A and B over the probability of B. This might not be at all intuitive when you first see the formula, but we'll see that it makes a lot of sense actually. So let's look first at what the denominator is and what the numerator is, and then figure out, well, if we put these two together, does it make sense to say that the probability of A given B is this formula? Okay, so we'll start with the denominator. What is the probability of A and B? Well, it's this red part over here. Okay, at least we know what we're talking about. What about the denominator, the probability of B? Well, it's all of B, right? So remember, then when we're saying the probability of A given B, we assume that B occurs. So actually, we can forget about the rest of the probability space and only think about cases where B occurs. So here I've reshaded the part of A and B in red because it's denominator, but actually we can get rid of the A in this case, right? It's just distracting us. So this is what the probability of A given B is telling us. It's saying we assume that B is true, right? And so we can forget all the rest of the probability space. We can forget the omegas and just focus on the B. And then look, in cases where B occurred, how likely is A to also occur? And so that's A and B, right? Because B necessarily occurred. And so the probability of A given B is going to be this shaded area, this proportion between the red and the blue of the area, right? And that's what we're representing here. So it makes a lot of sense because you're restricting your probability space to cases where B actually occurred because we're assuming it does. And then looking, well, in that, when we restrict only to B, how likely is A to also occur? Okay, so let's look again at the example. This is the example of the dice, right? When I tell you, I flip the dice and it lands on an even number, and then I ask you what's the probability that's also a high number? Well, let's write that mathematically. So what's the probability that it lands on a high number given that it lands on an even number? So remember, here, given that it lands on an even number means that you assume that that happened. And so you're restricting your space to this red shaded part of the diagram, right? I told you it landed on either a 2, a 4, or a 6. So by definition, this is equal to the probability that it lands on a high number and an even number over the probability that it lands on an even number. So right here, we just know how to do this, right? High and even, what are the only possibilities that are high and even in a six-sided dice? Well, they're 4 or 6, right? High is from 4 to 6, and low is 1 to 3. So the probability that it lands on a 4 or a 6 over the probability that it lands on an even number. And even numbers are 2, 4, and 6. Since they're mutually exclusive, right, the die can't both land on a 2 and on a 6, then it's easy to calculate these probabilities. The denominator is just 2 over 6, right? 1 over 6 for each side. And the denominator is 3 over 6. And so if you multiply that out, then you get 2 over 3. Calculating the conditional probability is going to be really useful for us to update our beliefs coherently or rationally. But let's not get carried away quite yet. Let's look at some other examples for now. So suppose I tell you that the probability that it rains in California is around 10%, so 0.1. And I'm representing raining in California as the rectangle, and, the possibility space is the rectangle, and R, the circle, is when it's true that it rains in California. And suppose I also tell you that the probability that it's less than 5 degrees Celsius in California is 0.01%. So it's 1% of the time. So it's very rarely less than 5 degrees Celsius. And here I put that, I represented it as the little C circle. So note that part of the C circle happens when inside R, which means that it rains and it's less than 5 degrees Celsius. And part of the C circle is out, so it's less than 5 degrees, but it doesn't rain. And suppose I also tell you that the probability that it rains and that it's less than 5 degrees Celsius in California is 0.008. So it's not 8%, but even lower, 0.8%. Right? These values aren't tracking the actual probabilities in the world. This is just for the sake of the example. And suppose I ask you, what is the probability that it is less than 5 degrees in California given that it rains? So note here that I'm not asking you the probability that it rains and that it's less than 5 degrees. I'm asking you, suppose that it's raining in California. In that case, what's the probability that it's less than 5 degrees? So how would you represent this? As we saw, the first thing we have to do is to say, well, the probability that it's less than 5 degrees given that it rains. That's how you write the question of what we want to answer. Right, we suppose that it rains and we want to know what's the probability that it's less than 5 degrees. Well, here it's going to be 0.008 over 0.1. Why? Because by definition of conditional probability, the probability that it's less than 5 degrees given that it rains is equal to the probability that it rains and is less than 5 degrees over the probability that it's less than 5 degrees. Look over at the definition that we gave you earlier in the video if you're not sure why. And those values are 0.008 and 0.1. So you divide them and you get 0.08, which is around 8%. So here's a question for you. Is the probability of A given B equal to the probability of B given A? And the answer is no. I'm going to leave it for you as an exercise to prove this after you finish this lecture. Okay, let's look at another example from a roulette wheel. All these examples are derived from kind of casino-themed examples, like roulette, dice, flipping a coin, but it doesn't have to be, but these are good to pump your intuitions. So the question is, what's the probability that a roll lands on a number between 1 and 10, given that it lands on a red? So in a roulette, you throw a little ball, it goes around the roulette wheel, and then it lands on a number, and there's numbers between 1 to 36, plus a 0, but we'll forget about that, and they're either black or red, and they alternate. So probability generally that it lands on a red is around 1/2, and that it lands on each number is 1 to 36. So now the question is, what's the probability that the roll lands on a number between 1 and 10, given that it lands on a red? Okay, so I told you, each outcome has a 1 in 36 probability. And I told you also the probability that it lands on a red is equal to that it lands on black, which is 1/2. So here, you have the tools to figure out how to calculate this, even knowing rather little about the roulette game. You know that the probability that I asked you for is equal to the probability that it lands on 1 through 10, given that it's red. So we expand our definition, right? So it's the probability that it lands on 1 through 10 and that it's red over the probability that it's red. So what's the probability that it lands on 1 through 10 and that it's red? Well, I told you that it alternates, right? 1 is red, 2 is black, etc. So that's going to be the probability that it lands on 1 or 3 or 5 or 7 or 9. These are mutually exclusive, so we just add them up. So that's 5 over 36. And so right now we have all the tools we need to figure out the conditional probability. All right, we have the 5 over 36, that's a numerator, and we have the probability of red already, which was given to us, which is 1/2. So we just plug that into the formula, right? 5 over 36 over 1/2, and we use a calculator, and that gives us around 28%. Okay, so, right, we have the tools to figure out a lot of questions about the conditional probability. So already we're seeing that our probability theory is becoming much more sophisticated and allows us to do many more things. So let's look now at the law of total probability, and then we're going to get an intuition for it, and we're going to see how these tools are going to allow us to not fall for one of the biases that I presented last week. So let's get started. So let's get to the law of total probability. What I'm going to do in this class is just state it for you and show you an intuition for why it's true. And we're going to use it as an exercise to prove why this is true. But we're not going to do that in this lecture because really you have all the tools you need. You just have to apply it. But I think the hardest part about this is to get an intuitive or at least visual understanding of this law. So the law states the following. The probability of A for any A is equal to the probability of A and B plus the probability of A and not B. And this is true for every A and every B. Okay, why is this true? So suppose that we have again our probability space with A and B. Where is A and B in this diagram? Well, it's in this shaded part of where the A and B intersect, right? And so if we want to know the probability of A and B, right, it's kind of the area of this red shaded part compared to the rest of the rectangle. Now, where is A and not B? Well, it's this blue part, which looks like a moon that's been bitten off of, or an apple. And so it's this blue part without the shaded red part. And so if we want to know what the probability of A and not B is, well, again, it's this blue area compared to the rest of the rectangle. So let's look at this equation of the probability of A and not B plus the probability of A and B. Note that this is just equal to the probability of A in the space. The probability of A is just equal to the blue shaded region plus the red shaded region. Note that these two are mutually exclusive. It can't be both true right now that A and not B is true and that A and B is true. So this is what the law of total probability says. It says that for any B, if we want to know what the probability of A is, then we'll just take the probability of A and B plus the probability of A and not B. Now let's take a case where A and B don't intersect. It's still true that the probability of A is equal to the probability of A and not B plus the probability of A and B. But note, not B is the gray shaded region, including A. So what's the probability of A and B? Well, it's not on the graph. So actually, in this case, the probability of A is equal just to the probability of A and not B, because A and not B is just equivalent to A. So this is what the law of total probability tells us. Equivalently, we can write this law as follows, that the probability of A is equal to the probability of A given B times the probability of B plus the probability of A given not B times the probability of not B. Why is that the case? Well, remember the definition of conditional probability. And this is also going to relate to Bayes' theorem, which we'll see in next class. But for now, just note that these laws can be rewritten in many ways. We've done a lot of hard work. We've gone over the 5 rules that are going to help us build our inductive logic. We've gone over the definition of conditional probability, and I've showed you briefly the law of total probability, right? And so now, let's put this to use and to help our reasoning. So remember that last week I introduced this bias of the base rate neglect. And I give you the following example. Suppose we have a reliable test used to diagnose a disease. 99% of people with the disease will get a positive test result, and 99% of healthy people will test negative. Now suppose that the general prevalence of the disease in the population, and this is called the base rate, is 1 over 100. And then I asked you, how likely is it that a random person who gets a positive test result actually has the disease? And I told you that this percentage was 50%. And you might find that weird because I just told you that these tests are really reliable, right? 99% is a very reliable test. Yet I told you that if we just pick a random person and they test positive, the probability that they get the disease, that they actually have the disease, is only 50%. So let's use the tools that we've learned to actually apply this. When tackling a problem like this, it helps to really put all the information we have on the table and be really clear about what the question is asking. So here I put it on the right side, and we know that what? That 99% of people with the disease will get a positive test result. I told you that. And I also told you that 99% of healthy people test negative. Apologies for the typo. The general prevalence of the disease in the population is 1 over 100. These are the 3 facts that I've told you. And the question I asked you is, how likely is it that a random person who gets a positive test result actually has the disease? Okay, so let's start, as usual, at looking at the question to answer and put it in probability form. This is going to be that the probability that the person has the disease, given that they test positive, right? I told you, how likely is it that a random person gets a positive test result? They get the positive test result, so that's given. How likely is it that they have the disease? So how probable is it that they have the disease given that they test positive? That's what we're going to care about. Okay, we can erase the question now because we know the value that we want to answer. What else do we know? We know that 99% of people with the disease will get a positive test result. How can we put that in probability language? Think about it for a second and try to do it yourself. Well, as follows. It's a probability that they test positive given that they have the disease is 99%. And that's what it means for a test to be reliable. It means that if I'm actually sick and I go and I take the test, then that test will come up positive 99% of the time. It doesn't mean that if I test positive, then that I have the disease with a 99% chance. So let's look at the second piece of information that we have, which is that 99% of healthy people test negative. What does that mean? Try to put it in probability form how we've done it. Well, it means that the probability of testing negative, given that you don't have the disease, meaning that you're healthy, that probability is 0.99%. Note that it's not saying that if you test negative, then the probability that you don't have the disease is 0.99%, but rather that if you're healthy, then the probability that you test negative is going to be 0.99. And testing negative here just means not testing positive. So it's important to be very careful when you read the prompts to put these probabilities correctly, right? So let's read it again. 99% of healthy people test negative. Okay, that means people that are healthy, which don't have the disease, if they take the test, then the probability that they test negative is going to be 0.99. Now let's look at our last piece of information, and this is that the general prevalence of the disease in the population is 1 over 100. So how do we put that in our probability notation? Well, that just means that the probability that you have the disease is 0.01, right? It's a probability if you pick any random person in the population, the 1 out of 100 of those will have the disease. It has no condition, so we don't need to worry about putting any conditions. So now we have all the information put into probability notation, if you will. Here's an exercise that I highly recommend you pause the video and do now. Find the probability of having the disease given that you test positive. You already know the answer, which I gave it to you, which is 0.5. But why is that the case? You have all the tools, so I recommend you pause it, try, and only once you get stuck, then continue the video, which we're going to go through it. Okay, so we'll go through it now. So we want to know the probability that you have the disease given that you test positive, and I put the information in the bottom right corner. Let's simplify the notation a little bit here to the probability that you have the disease is DIS here for disease, and testing positive is POS, positive. Note that testing negative just means not testing positive, and being healthy or not having the disease is just not having the disease. Okay, so the first thing you should do here is expand this formula using our definition. The probability of having the disease given that you tested positive is equal to the probability of having the disease and testing positive over the probability of testing positive. This is just by definition. So, seems easy, right? We just have to find the numerator and the denominator, and we plug it in. And that's what we're going to do. So let's look at the denominator, the probability of having the disease and testing positive. So we're going to do the same thing here. We're going to expand using the definition. The probability of having the disease and testing positive is equal to the probability of testing positive, given that you have the disease, times the probability of having the disease. Why is this the case? Why is this true? Well, try dividing both sides by the probability of having the disease, and then you'll just have the definition of what it means for the conditional probability of testing positive given that you have the disease. So the trick here was expanding the probability of having the disease and testing positive using the definition of conditional probability. But once we do that, we actually have in our assumptions, we have everything we need, right? We know what the probability of testing positive given that you have the disease is, that's 0.99, and we know what the probability of just having the disease is, which is 1 over 100. These were given to us. So we just replace it, right? They're highlighted in green here, and we get that the result is 99 over 10,000. So we're done with the denominator. Now let's move to the denominator. And this is going to be a little bit more complicated. So what is the unconditional probability of testing positive? Right? So if you pick a random person in the population, what's the probability that that person is going to test positive? Well, we don't really know how to do that. We don't have it in our information. But here's a trick. Use the law of total probability. We know by the law of total probability that the probability of testing positive is equal to the probability of testing positive and having the disease, plus the probability of testing positive and not having the disease. Think about this intuitively. If you pick anyone randomly from the population, the probability that they test positive, right? There's only two possibilities. Either they test positive and they have the disease, or they test positive and they don't have the disease. So the law of total probability allows us to expand this probability of testing positive into this formula. And let's use this to our advantage. We already found out earlier what the probability of testing positive and having the disease is. It's 99 over 10,000. So we can just replace that with what we know. Now let's try to find out what the probability of testing positive and not having the disease is. Right? This is not a conditional probability. It's the conjunction of both testing positive and not having the disease. Well, this is going to be a little bit more complicated. Let's do our trick again of expanding. But in this case, it's not really obvious how you're going to do it. So when you're doing the exercise, you might have tried out a few different methods. But here's one where we actually are going to add the probability of testing positive and not having the disease, which is what we're trying to find, plus the probability of not testing positive and not having the disease. And we know by which law that this is equal to the probability of not having the disease. Which law are we using? Yeah, it's the law of total probability, because note that here we're looking at the probability of not having the disease is equal to the probability of not having the disease and testing positive, plus the probability of not having the disease and testing negative, or not testing positive. Okay, so why are we doing this? Well, because it's easy to find out what the probability of not having the disease is. Let's do it, right? The probability of not having the disease is just 1 minus the probability of having the disease, right? I'm using P and PR interchangeably here. In standard probability, we actually don't write PR, so I'm slowly going to ease our way out of it. But so here, the probability of not having a disease is 1 minus the probability of having the disease. And that's just 1 minus 1 over 100, which is 99 over 100. Remember that we proved this formula in the last lecture. So we can replace that into the equation above and go on. But we're not done yet, right? What we're trying to find is the part highlighted in green, the probability of testing positive and not having the disease. But we still need to figure out this part highlighted in yellow. What's the probability of not testing positive and not having the disease? What are we going to do? Well, here we put it here. Can we expand it with the law of total probability or with the conditional probability? Well, let's move the assumptions here. And yes, we can use the definition of conditional probability again, right? Try doing it yourself. And we have that the probability of not testing positive and not having the disease is equal to the probability of not testing positive given not having the disease times the probability of not having the disease. Why is this the case again? Well, try dividing up both sides with the probability of not having the disease. And then that's just the definition of conditional probability. Why are we doing this? Because we actually have the information of what the probability of not testing positive given not having the disease is, right? This was given to us in the assumptions. It's 0.99, so it's 99 over 100. And we also just figured out what the probability of not having the disease is, right? Just a little bit before, which was also 99 over 100. So we multiplied these with our calculator, and it's 0.9801. So now we found the highlighted yellow part, we just replace it in the equation, and we're almost done, right? Because now we can know what the probability of testing positive and having the disease is. We just use some simple algebra. We subtract both sides by 0.9081, and we get that the probability of testing positive and not having the disease is 0.0099. And this is just the same as the highlighted green part, so we can replace it in the equation above. And so we know what the probability of testing positive is. We just add it and we get 0.0198. We're not done yet, right? Because we found the denominator, but now we still have to divide the numerator from the denominator. So putting everything together, we get that the probability of having the disease, given that you test positive, is equal to 99 over 10,000 over 0.0198. And just put that in the calculator, and you get that that's 50%. Magic, right? So what these conditional probabilities and the tools that we've seen, they allow us to really not make mistakes in these very complicated cases where you have to keep all of these almost puzzle pieces together. Okay, so we've seen how to use probabilities and conditional probabilities. We saw the law of total probability, and we've used these two to apply them into a case where humans tend to make mistakes that we've seen before, right? This is the case of the base rate neglect. And we've saw the example, the surprising fact that given quite reliable tests, if you just pick a random person and they test positive, actually the probability that they actually have the disease is probably going to be much lower than you initially suspect. So probabilities allow us to reason better in this way, and we'll see how to apply them in other examples as well. And in next class, we're going to look at Bayes' theorem, one of the most famous theorems in probability theory, and we're going to see how probabilities relate to belief. But here's a little taste of that. One way, but not the only way, of justifying our beliefs is by first operationalizing our degrees of belief with betting behavior. So you might have gotten a sense of that with the examples I've been giving of flipping a coin, of roulette tables, of dice. These are just cases where the beliefs can be really quite clear and we can really say that we assign probabilities to them. And so what we're going to do in this class is operationalize degrees of belief with betting behavior and then see if there are rational beliefs that we can have and irrational ones. And as we'll see, it gets quite interesting. You might think that it's a little weird to talk about our degrees of belief as if they were betting behaviors. But as we'll see, in science we practically never actually measure the thing we're talking about, especially not in the social sciences. For example, if you've seen some news articles that say, well, maybe Finland is the happiest country on earth, right? How are they measuring happy? You can't measure people's happiness by going on their brain, or there's no such thing as happiness. There might be ways to determining whether people feel more happy or not by operationalizing happiness in different ways. For example, you might look at the stress levels of a population, or you might see how people respond to questionnaires. None of these measures are perfect, and it's going to be the same thing with operationalizing degrees of belief. Operationalizing them as betting behavior is not perfect for all contexts. But for many contexts, it's really useful, and there are clear ways where there are some rational beliefs that you can have and irrational. And this is going to be our stepping stone, which we'll see in next class. Thank you very much.